So let us start with the basics of secure communication. Cryptography or cryptology is the science and art of sending messages in such a way that they cannot be eavesdropped, that they are protected. So the whole art of protecting information has a long history, and one can give a series of lectures about it. But instead of going into all details, let me just describe the only safe way of communicating. It is a relatively simple system known as a one-time pad, which is very easy to explain, and it also allows me to introduce the basic concepts of secure communication, the notion of cryptographic key. So say we have two individuals, Alice and Bob, surprise, surprise, and Alice would like to send messages to Bob, and she would like to protect those messages in such a way that no third party, no eavesdropper can eavesdrop, read, intercept messages, read and learn what kind of secrets Alice would like to send to Bob. Most attacks in cryptography are based on statistical analysis. As it happens, any natural language has a natural frequency of characters, so the letters in the alphabet, if you write a regular text, are just not randomly selected. There is a pattern to it. So one way for Alice to communicate in a secret way is to find a method where she can just wipe out this statistical pattern into the different characters. So we assume that Alice is going to use binary alphabet, so a sequence of zeros and ones. So say that this is a message that she wants to convey. I know it doesn't look very appealing, perhaps. Whatever it is, just there is a message that she would like to send to Bob. It is written using a known binary alphabet, some sort of ASCII code, you name it. So that's something that anyone can actually, with having enough messages, can actually apply statistical analysis and figure out what it is. So that is a clear text, something that cannot be just sent over any public channel, because it will be obvious what Alice is trying to communicate to Bob. But instead, what Alice is going to do, she's going to pick up a random sequence of zeros and ones. So let me just try to say that this is this sequence called a cryptographic key. So let's call it K. Now, this sequence is just randomly generated. So it's just it's equally likely that you get any other sequence of this length. So it's chosen, each bit is chosen uniformly with probability half, say. So now what Alice is going to do, she's going to perform addition modulo 2. So she's going to add the message to the key bit by bit. So it goes like this: 0 plus 1 is 1. 0 is 0. 1 plus 1, that's modulo 2, is 0. 0 plus 0 is 0. 1 plus 0 is 1. 1 plus 0 is 1. 0 plus 1 is 1. So now this thing is the cryptogram. By doing this addition, Alice managed to just wipe out completely any statistical pattern that may exist here. So what you get here gets randomness, and that randomness comes from the cryptographic key. The cryptographic key itself has no meaning. It's just a random sequence of characters. Now, Alice is going then to send over any public channel, so it could be a broadcasting or anything, the whole thing to Bob. So Bob gets the cryptogram, which is 1, 1, 1, 0, 0, 0, 1. And then Bob thinks, what does it mean? Well, I have this secret key that I share with Alice, so let me just try to figure out. So Bob picks up the key, which is identical to the one that Alice has. It goes like 1, 0, 0, 0. 1, 0, 1. So Bob gets the cryptogram, gets the key, and does exactly the same operation as Alice did. But this time it's a decryption. So this was encryption, and this one goes, even though it's the same operation, it's just it revealed the original message. So it goes like 1 plus 1 is 0, 0 plus 0 is 0, 0 plus 1 is 1, 0 plus 0 is 0, then we get 1 here, and 0 here. So here we have 0, 1, 1, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0. So that's the message. So you see what happened here is that Alice encrypted by bit addition, and Bob used the same operation to decrypt and get the message. Now you can prove, it's again a relatively simple proof, that as long as the key is truly random, so we request from the key that is indeed truly random, and as long as it is secret, it's not known to anyone but Alice and Bob. So it has to be secret, right? Makes sense. And as long as it is used only once, then the whole system is perfectly secure. There's no better way of eavesdropping or cracking the system than just simply a wild guess what the message can be. I think that it's clear what the randomness makes sense, right? Secrecy makes sense. Now, it has to be used only once, as if we start reusing, if Alice and Bob start reusing the same key, then it's not good, because then sooner or later a pattern will be found. Now, this then indicates a kind of a problem that we have with this system. For every single message that Alice wants to send to Bob, she needs the key that is of the same length as the message. So you may sort of think, well, fine. But then the problem is that Bob needs the key that is identical to this one. So there is a need to generate lots of random secret numbers. So how is it then possible? Of course, you may say, okay, Alice and Bob one day meet, they get together, they just generate a huge random sequences of numbers, and Alice goes into one location, Bob travels somewhere else. So they have those keys. But you see, those sort of long keys will be very quickly depleted, because when they start communicating using this key. So there will be a need to generate new keys and distribute them to Alice and Bob. And that is a big thing, because those keys have to be secret. So how are we going to distribute the key in such a way that Alice and Bob will get the same
random, completely meaningless string of bits?